Okay, so our problem is for 147. Now let's read the question first. Determine the length B of the triangular load and its position A on the beam such that the equivalent resultant force is 0 and the resultant couple moment is 8 kilonewtons meter clockwise. Okay, so now we have two loads. One is 4 kilonewtons per meter, okay, at peak point, and the other one is 2.5 kilonewtons per meter at the peak point, so at point here, at this location. It is acting on a beam connected to a wall. It's fixed to the wall. On the other hand, the length of the beam is given as 9 meters. Now we have a point A here, so the lower triangular load ends at point A, and its magnitude is decreasing linearly, as you see. And the upper load is 4 kilonewtons per meter. Again, its magnitude is decreasing linearly, and moreover, it acts on a length of B. The lower 2.5 kilonewtons per meter load acts on a length of B plus A. Now, it is told us that the resultant load is wanted to be 0. This basically means that area under this curve or area of this triangle and this triangle is wanted to be equal. As a result, resultant force generated by this distributed load and this distributed load will be equal. So let's solve the problem. So these are the given. Now first we are wanted first calculate the magnitude of the resultant force of each distributed load. First is FR1. So remember that the magnitude of the load is 4 kilonewtons per meter. It acts at a length of B. Therefore, the area under this load is 4 times B divided by 2, and it makes 2B. Okay, FR2 is equal to, so the peak magnitude is 2, as you see here. Therefore, the area under this distributed load is 2.5 multiplied by B plus A divided by 2, which makes 1.25 B plus A. Sorry, it's here. Okay. Now, it is wanted that FR1 plus FR2 is 0. Since FR1, the direction of FR1 and FR2 is opposite, we can easily say that 2B minus 1.25 B plus A is equal to 0. From here, we can find that A is equal to 0.6 B. Okay, this is what is wanted. Now, next thing is the moment generated. Now, in order to find the moment generated by these forces, we have to choose an origin. In fact, it might be much more convenient if we choose this point as the origin. In fact, FR1 will act B divided by 3 at the location of B divided by 3, and FR2 will act at B plus a divided by 3, because this is the base of this point will be the base of the triangles which are generated by the distributed loads. So FR2 is acting at a point B plus A divided by 3 from the free end, and FR1 is acting at the point at a distance of B divided by 3 from the free end. Okay, now the point is moments generated by these forces has to be equal to 0. In fact, we know that not generated by they have to be equal to 0. They have to be equal to 8. Now this basically means that FR1, so this one, multiplied by B plus A divided by 3. So I'm calculating this distance. Okay, B plus A divided by 3 minus B divided by 3 has to be equal to 8, because the magnitude of FR1 is equal to magnitude of FR2, as you remember, right? This basically means that FR1 is equal to FR2, and they generate a force couple. And remember that moment generated by the force couple is the magnitude of one of the forces multiplied by the distance between them. So if I write it, I know that FR1 is equal to 2B, right? B plus A divided by 3 minus B divided by 3 will give me A divided by 3. And it has to be equal to 8. Now, I know that A is equal to 0.6B. I put it here. Now, this basically means that 0.6 divided by 3 is 0.2, or 1.2 divided by 3, or in other words, it is 0.4. If you divide 8 by 0.4, it makes 20. And in fact, B square is equal to 20. From here, we can find that B is equal to 4.47 and A is equal to 2.68 meters.